All right, so we're still studying polynomials, and we're sort of paralleling a lot of what we did in Chapter 1 with the integers. So what we're ready for now is the definition of the greatest common divisor of two polynomials. So my polynomials are f and g. A greatest common divisor of f and g has to be a polynomial d that divides both. That's part one here. 2 is the greatest idea, but we're doing it a little bit differently. So instead of saying it's like with the integers, it was the largest integer that divided both. Here, we're going to use a property that we saw back in Chapter 1, but it was a corollary. It wasn't part of our definition. It was corollary 1.7 that said something like this. So what it says is, if you have some other divisor, then it divides the greatest common divisor d. And I said the greatest common divisor. I should not have been saying that because notice the language here, a greatest common divisor. That's using the word instead of the for a very particular reason. So let's look at an example here. If I wanted to think about the greatest common divisor of two polynomials, let's say x squared minus 1 and x cubed minus 1, I want to think about things that divide both. So x minus 1 divides both, and it's there isn't a squared divisor that divides both. X minus 1 is kind of the biggest you're going to get, maybe in terms of the degree. It's the largest degree polynomial that you're going to get that divides both. But the problem is that so does like 2x minus 2. That divides both also. You just have to factor out an extra 2, leaving a 1/2 in there after you've pulled it out. And we could do that in lots of different ways. So I could factor out a 1/3 minus a third, well, sorry, 1/3 x minus a third if I wanted to, and lots of other things. So a greatest common divisor of two polynomials is not unique because any common multiple of it, any constant multiple of a greatest common divisor is also a greatest common divisor. So the GCD of two polynomials is unique only up to constant multiples. And so we can use this language of a greatest common divisor, or we can say the greatest common divisor is unique up to constant multiples. All right, so now that we know how we define a greatest common divisor, so it's a divisor so that any other common divisor divides it, so that's the sense in which it's greatest. We have a bunch of results that track really closely with stuff from Chapter 1. So relatively prime is the first one. So two polynomials are relatively prime if one is a GCD of the two polynomials. So this is similar to relatively prime integers that we saw back in Chapter 1. The lemma, I think this is one that we didn't really study in Chapter 1, but it says if f divides a product of g times h, and if f and g are relatively prime, then what you know is that f has to divide h. So this is a lemma that showed up in Chapter 1 also. I don't think we mentioned it there, but we're going to look at it here, and I may have you prove it for homework. The theorem is one that should feel really familiar too. It's very similar to something from Chapter 1. So this was another way to characterize the greatest common divisor. So if we have two polynomials, f and g, and we define this set of all linear combinations of f and g. So it was a times f plus b times g, where this should be at times, I'll fix that, where a times f plus b times g is not the zero polynomial. So we take all the linear combinations that don't give us 0, and we choose a d out of that set of least degree. Okay, and if we do that, then d out is a greatest common divisor of f and g. So we did the same thing with the integers. In that setting, we had like, I don't know, AM plus BN or something. And we took all the positive ones and we chose the least out of the set and said that was the greatest common divisor. So I'm going to have you look at this theorem and compare it to chapter 1 also for homework. In chapter 1, we did prove this theorem, and the proof here is very similar. So I'm going to go through that. And last, so this corollary kind of puts the three ideas up above together. So it says, if f and g are relatively prime, that means 1 is a GCD of them. Then that means that 1 would be in that set S from up above. And so it means that we can find polynomials a and b so that af plus bg equals 1. And if you remember, this is where in chapter 1 we used the Euclidean algorithm to find that a and that b. And this was the corollary that sort of translated to those bucket filling problems. So that was something else that we saw back in chapter 1. All right, so for homework, I'm going to have you draw some parallels between these results and what we saw in chapter 1.